right. Welcome to United Astronomy Clubs of New Jersey. So, unfortunately, because the expected weather for tonight was supposed to be thunderstorms and very unpleasant weather, we did cancel our in-person program where we would have uh, you guys as the public up on our site in Jenny Jump State Forest. We, however, are still offering this online and will continue even if we have inclement weather uh, to offer the live streams regardless. With that, you're always going to want to check out our website, uacnj.org, and also our Facebook, where we will be announcing if there's any changes to the plans, because unfortunately, astronomy is very much dependent on what the weather is. With that, like I said, check us out on our website and our Facebook. We also have Instagram, Twitter. We have a Discord channel that's up and coming. Uh, United Astronomy Clubs of New Jersey is a nonprofit, and we've been very thankful that we have been able to continue offering these free public programs through the donations from you guys as the public throughout the pandemic, and also with all our volunteers with their time and efforts to keep everything running with the lights on. Um, if you want to donate, you can get details on our website. Uh, we have Amazon Smile donations, we have Patreon, um, as well as other options that you can check out there. Tonight's presentation is going to be Anatomy of a Star with Paul Fischer. Paul Fischer has a bachelor in chemical engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though always interested in celestial objects, Paul's official start in amateur astronomy was one night 8 years ago, lying in an awkward position on his roof in the freezing cold, holding a pair of binoculars. He caught a brief, clear glimpse of the Galilean moons of Jupiter and was hooked. After some introductory reading, he purchased his first telescope. He is now an active member of Northwest Jersey Amateur Astronomers and a consistent volunteer at United Astronomy Clubs of New Jersey, and is actually currently our president on our board. He still frequently manages to find himself outside at night, still in awkward positions, staring up at all the neat things in the night sky. And with that, here's Paul.
Hello, everyone, and hopefully you can see my title slide, The Anatomy of a Star, and it does have NWJAA and UACNJ up there, as Kim mentioned. And thank you, Kim, for the introduction. And just so Kim did hesitate a little bit. Stevens Institute of Technology does give a little bit of a weird degree. I have a Bachelor of Engineering, which not a lot of people have heard of. So yes, the BE throws people off a little bit. So that is that story there. The Stevens is a little bit weird compared to other schools. So let's get started with the anatomy of a star. All right, just as anything else, we're going to do a little bit of introduction as we get into the presentation tonight. We're going to talk about a little of the who, what, wheres, and whys. First of all, who's to blame? I like to give credit where credit's due and take responsibility for my preparation of these slides. First of all, the first gentleman there listed, Kenneth Lang. I read this book, The Life and Death of Stars, and that information's up there. Also, a lot of information, background information in astronomy in general from a video course. It was an introductory type of course from Dr. Alex Filippenko, who you may or may have be familiar with some of the programs that he has, some of the television programs and commentary he has done, as well as being a known professor of I'm going to say astronomy, but it might be cosmology. I'm unfortunately not exactly aware of his exact title, but well known in the industry. And in any mistakes, of course, I take that. I did prepare these slides in this presentation, so any mistakes, don't lay them at the feet of these two gentlemen. Those are my mistakes. So what are we going to cover? We're going to cover an introduction to a particular star. We're going to learn a little bit about the insides, the mechanical workings of the star. We're going to find out a little bit about how stars come to be in the first place. We're going to talk a little bit about the mechanisms, what's driving the massive amounts of energy stars are pouring out. We're going to talk a little bit about the one star we're going to talk about compared to other stars in our universe. And then we're going to talk a little bit about what happens at the end of a star's life. Introducing the sun, and I have a subtitle there, sort of. And why are we doing that? Well, we're doing that because our knowledge of stars is based both on our own star, the sun, and other stars in the universe. So there are advantages and disadvantages to studying our sun and stars in the universe. Let's get this question though out of the way first. Yes, our sun is a star, and other stars could be considered the suns of their own planetary systems. However, in this thought, we must be of two minds. When compared with data from and other measurements of other stars, the sun is really kind of average and unremarkable. However, our sun is emotionally, historically, geologically, evolutionarily, and physically indispensable to us. So to us, it's the most important star in the universe. So is the sun a special thing? To us, it's very much a special thing. As far as the universe, the rest of the universe is concerned, it is a relatively average star. And then why is our model today, or our sun, our model, which we're creating after the sun, why is that sort of what our model is? Well, because astronomers are actually actuaries. And that, of course, is a good tongue twister, but it describes well what are the thought are how the information that we know about stars has come about. One thing to keep in mind is that the sun has been around for 4.6 billion years. We, as a race, and our history certainly has not been around anywhere near 4.6 billion years. So we have not seen the beginning of our sun, nor have we seen the end of the life of our sun. So if we base our knowledge totally on our sun, then we have a very limited view of what's going on. But when looking at stars, astronomers not only have to take into account the speed of light and the expansion of the universe, but also their statistical variation. It's not a bug, it's a feature. In other words, we get to see out in space the beginning, the birth of stars. We also, looking out into space, get to see the end of life of stars, and stars that are both very different from our, or different in many ways from our sun, but also stars that are very similar to our sun. And so, therefore, we get a lot of knowledge about the totality of a life of a star like our sun. So it's not a bug; it's a feature. To having to do these calculations, getting to see back in time because we're looking at incredible distances. We are our our understanding is increased by both by seeing further out into space and getting this statistical knowledge of stars. But it also works both ways because the sun for us has some extreme logistical advantages. Our sun is very close to us, therefore we can study it or much more in depth than we can study a more distant star. Uh, therefore, our model for today, how we're talking, our star is actually a very sun-like model. It's maybe not a stretch to consider our sun an every star. Uh, so far I've hit you with a lot of text. Let's start here for for our first picture. This is, I found, a good resource, especially as the sun is becoming more active in this solar cycle. The Solar and Heliospheric Observatory, SOHO. You can find it at on the second line here at that address. I made it current as of today. Normally, I assign this as homework, but today, because there's actual interesting things to see on the sun, well, not right now for us here on the East Coast, but you can. There are interesting features on the sun at the moment. Taking a look at the HMI, it's what you can see with a standard solar filter. So again, just remember there's a safety issue. Do not point your eyes, or definitely don't point anything that can magnify at the sun without without a rated solar filter. So here it is from SOHO. This is the sun current as of today, and you can see three named regions, and you can see these guys right on the limb here of solar spots on the sun. If you have a Bader white filter like I have, you could point your telescope to the sun and see these self-same sunspots right on the sun. And what's interesting, at least I'm finding it interesting, is that these sunspots where even a year ago, and definitely 2-3 years ago, when I first got the filter, you would point your telescope at the sun and see nothing on it as far as sunspots go. So now we are seeing more sunspots, and you might have been reading more about sun activity in the news. Let's talk a little bit about the inside scoop, the makeup, statistics, and structure of the sun. What is a star like our sun made of? First, we need to know in astronomy, metals are any element that is not hydrogen or helium. So to an astronomer, the universe is made up of three categories: hydrogen, helium, and metals. The Big Bang created mostly hydrogen and some helium. They are by far the most abundant elements in our universe. And this chart here that I made up is the approximate concentration of our universe. Hydrogen mostly, at over 70%, helium at about 30, and the remainder, which is everything else, at about 1.43%. But metals isn't really satisfying to us, is it? We want to know a little bit more about what that other stuff is. And here, if you notice here, if I can, this is a spectrograph. This spectrograph is will show you various due to the properties of light given off when electrons change their orbital in their in their structure. They various frequencies of light is given off, and those various frequencies can be absorbed by elements, gas that happens to be in the way of the source of light. That source of light being our sun. So these black lines are absorption lines, and these absorption lines are where that specific frequency is absorbed by that molecule, and that molecule, that orbital that the light is hitting, is compound or element specific. So by knowing where those absorption lines are, we can tell that these black lines are telling us what is in our sun. Over here, a little bit of abundance of the elements in our sun. You can see here that again, hydrogen, this is a logarithmic scale. Hydrogen and helium are way up at the top as the universal makeup would suggest. And then these, you can see carbon, oxygen, nitrogen, and going down here are your various elements. As the atomic weight goes up, the abundance goes down. You can see here lithium and a couple of other elements, though, seem to be missing. And we'll get a little bit into why that is. Generally, that's universal too. These elements are not created in the same way that these elements are, certainly, and then more they're created like these elements are, which is why they happen to be down here in the same range. All right, so let's play a game. We're going over the numbers here of our sun model. Try to compare these values to something you know here on Earth. The core temperature is 1.56 times 10 to the 7th K, and 0 or water freezing is at 273 Kelvin. Yes, Kelvin instead of Rankine. Yes, Kelvin. So so it's at 0. It's at 0 Celsius at 273 K. So that's quite a bit, 10 billion times more than that, right? So quite a bit hotter. Excuse me, let me say that again. It's 10 million times hotter. Core pressure, atmospheres. 1 atmosphere, of course, is where we are here on planet Earth. Mass, obviously, again, almost 2 times 10 to the 30th kilogram, where 1 kilogram is about 2.2 pounds here. Diameter is over 1 million kilometers. The distance to our sun is about 93 million miles. That the definition here you can see of an AU is the distance from the Earth to the sun. And the distance in light years, it's 10 to the minus, what is that, 4 zeros, so 1.6 times 10 to the minus 5. And the energy, of course, is just incredible coming out of the sun. In fact, if you were to think about the sun and the energy output, I want you to think about today on this rainy night, sitting in front of a campfire outside. Maybe you're 10 or 20 feet away from that fire, and you can feel the heat of the fire on your face, and that's why you're sitting there, because that fire is comfortable in that region. Well, here we are, comfortable uh, at the distance of 93 million miles from the sun, and you can feel it when you tilt your head up to your face up to the sun. You can feel it. So 93 million miles away, you can feel the sun on your face. That's how powerful this entity is. So what is in the sun really? What is what is that stuff the sun is made of? The sun is an incredibly hot, incredibly massive, is incredibly hot, incredibly massive, and under gargantuan pressures. It's not made up of matter that we experience here at Earth. It's a forced state of matter called plasma. Mostly, this plasma is made up of hydrogen nuclei, we also known as protons, helium nuclei, which are also known as alpha particles, and free electrons. Plasma is a fluid. So if you remember from physical science way back when, fluid has the properties or includes both liquids and gases. It also includes this fourth state of matter, plasma, and even if plasma is still a fluid, even if it's extremely dense at the core of the sun. The average density of the sun is 1.41 grams per cubic centimeter. Water is 1 gram per cubic centimeter, but at the core, the sun is greater than 10 times the density of lead. Still a fluid, though. Very interesting. Here's the solar structure, what the inside of the sun looks like. The interior structure of the sun is revealed by helioseismology. It's similar to how geologists use seismology on the Earth. How do we know what's inside the Earth? Well, we can make calculations based on how waves travel and how we detect them on the other side of the planet through various places on the planet through various sensors placed on the sides of the planet. So low frequency, powerful waves, earthquakes traveling through the earth. That's how we do it. Well, we can't generate anything like an earthquake here on Earth. Well, we can do some things that register seismically, but here on Earth, but we can't do it for the sun. But the sun has its own events happening on it, and watching those events and see the reactions on various portions of the surface of the sun is how we understand a little bit about what's going on inside the sun. And I'm just going to advance this real quick here. Nope, I'm going to talk right off of this side. Here are some of the things that we want to know. The sun has a radiation zone. It has a core, of course, that we talked about, a radiation zone. That radiation zone is where the fluid around it is not still, but relatively what we call, I guess, quiescent, where there isn't say a boiling mass, but a more slowly moving fluid inside, and then a convective zone where large chunks of the sun move up and down and back and forth. Those are the three main zones inside the sun: the core, the radiative zone, and the convective zone. Some features that you may have heard of on the sun, their prominences coming off of the sun, flares coming off of the sun, the corona, which is the bright, very bright light around the sun, the chromosphere, which is the this the excuse me the where the color, where we're getting those colored absorption bands on the sun, the a coronal hole, the photosphere, the visual surface of the sun, and sunspots. The sun is a magnetic dynamo, and so we're aware that the sun has a magnetic field. This magnetic dynamo is how that field is developed. And how does that happen? Well, we go from a solar minimum to a solar maximum and back to a solar minimum in about 11 years. The solar minimum is when the lines are basically not pulled apart too much. They are relatively unstretched. As time goes on, the lines get stretched, and then we reach a maximum where the lines are really twisted around the sun. And now, what causes this twisting? So what happens here is at the equator of the sun, as my cursor moves across in each of these various time periods here, the equator moves at a different speed than the polar regions of the sun. So what happens is that this equator is racing a little bit, and the polar is going a little bit slower. So the equator region starts pulling these charged particles, the plasma that we know, in comparison to the polar regions. So, and what do we call when we move these charged particles? When you move charge, it is a current. And when you induce a current, you, of course, induce magnetism. So that's how the magnetic field is generated on the sun. These differences in the plasma moving at different rates on the sun is what causes the magnetism on the sun. So therefore, the sun is a magnetic dynamo. As I said before, the solar cycle is 11 years long from solar minimum to maximum, and of course, a full cycle goes all the way back again to let's see, we started there from the minimum. So minimum to minimum is 11 years long. It was originally discovered by recording the frequency of sunspot activity. So people in ancient or older times noticed the sun spots and recorded them and left records. Flares, sunspots, coronal mass ejections, coronal holes, and other solar surface and atmospheric phenomenon all vary with the solar cycle. It's important to study and predict these solar events and the space weather to protect our electrical infrastructure, our satellites, and our astronauts, as more and more we are becoming a spacefaring race. Okay, how is a star born? Let's take a look at how a baby star is born. Okay, be very quiet for the next few slides. Don't wake the babies. That's a stellar nursery there. Here's some more stellar nurseries. Can actually see the light from the stars there. New stars being born. Here's some protoplanetary disks. These are stars in the very center. And actual planets clearing out. They're clearing out the dark spaces there, clearing out their orbits. What is a stellar nursery? A stellar nursery is a cold, dense, massive nebula, a cloud in space of molecular hydrogen, mostly molecular hydrogen. Cold means about 10 degrees above absolute zero. Massive means that these clouds are tens of light years across. The clouds, in order to be a stellar nursery, it's needed for them to be that size to protect the nursery, the star nursery, from disruptive cosmic radiation. Regions can collapse spontaneously if they meet a specific criteria. And I wrote myself some notes here. What is this specific criteria? It's the gene's mass. What is the gene's mass? In words, genes is derived from a comparison of time it's a ratio or a comparison of time constants, and those time constants have to do with the measurement of densities and mass inside a given radius. So what's happening? The more mass you have the more densely packed with mass you are in a given radius, in a given volume, the more likely it is for that cloud to begin collapsing. And if, of course, you have this disruptive cosmic radiation that the rest of the nebula is protecting you from, then that mass will break up or whatever and not meet this gene's criteria. If it does meet this gene's criteria, then it will begin to collapse. But collapse doesn't only happen by meeting just a specific density threshold. Collapse can be assisted by perturbations from external events outside the cloud, a passing star, a nearby energetic event, or even cloud collisions. If those things happen, you can obviously get some sort of internal compression and thereby meet the criteria needed to start collapsing the cloud. But regardless, collapse begins and a protostar begins to form. So what is a protostar? The protostar is different from a regular star in that the protostar is heated by gravity collapse. It has not yet started nuclear fusion. Remember to think about what's going on as the star collapses, as the gas starts collapsing into the protostar. Remember conservation of energy. It's a law. Potential energy of the gas collapsing, that is the gravity attraction associated with the mass, it starts getting converted. What's it converted into? It's converted into kinetic energy, which is the bulk motion of gas inward. Also, there's rotational energy associated with it, but also enthalpy. Heat energy and pressure pressure energy. So heat energy and pressure energy increases as the kinetic energy increases as the potential energy is getting converted. If the protostar is massive enough, eventually that hydrogen fusion can be sustained. In other words, all that kinetic and enthalpy, kinetic and energy and enthalpy are sufficient to heat our gas so that fusion can start. At that point, collapse is halted. A hydrostatic equilibrium is reached and a new star is born. What's hydrostatic equilibrium? You notice the star on the last slide for hydrostatic equilibrium. What is that thing? Well, hydrostatic equilibrium is when plasma pressure pushes out and gravity pulls the mass in. So the pressure of the heated material, the fusion giving it energy, that pressure pushes the gas of the star out, the plasma of the star out, but gravity keeps uh, pulling it back in. So there's you imagine we went over the amounts of energy a little bit earlier. What's causing, I mean, that's titanic amounts, but why is it stable? Uh, why is it not those amounts of energy happening? Why is it not blowing up one way or the other? Remember, a collapsing fluid heats and an expanding fluid cools. So what does that mean for us? The changes in the rate of fusion are opposed by changes in plasma expansion. So if the star for some reason were to get a little bit bigger, the rate of or excuse me, if the star were to get a little bit hotter, the let's say the rate of fusion increased a little bit, the star would expand. If the star expands, the temperature ends up going down, which ends up changing the rate of fusion back down to the level it was at. Uh, so the star expanded because it got hotter. It expanded, so the temperature of the star cools. The cooling star creates now um, a slower fusion rate. It starts to contract. Once it contracts, it starts to heat up again and push back out. So it's self-correcting in that manner. The star we would not be here if these two titanic forces were not only balanced, but had some sort of self-correcting mechanism associated with it. Let's talk a little bit about this hydrogen fusion that is going on in this star that's providing the heat to keep the gravity from collapsing all the way. So sometimes this uh, fusion, the science behind the fusion makes a lot of sense. Stuff that we can look at just at our experience level here on Earth and say, oh yeah, that makes a lot of sense. So this here is a Maxwell Boltzmann distribution, and it's showing that larger kinetic energies, the larger the kinetic energy, the more heat is associated with it, the more energy it has. The number of particles with that kinetic energy. So this is a distribution. There very low zero kinetic energy that's at zero. There is this average value or this median value here, and then or mode value here. And then as you get higher and higher kinetic energies, it drops off in a curve like this. The white area shows the proportion of particles in the sample that do not have enough energy to slam together and cause a fusion reaction. This dotted line here is the activation energy, the minimum required, and the blue area shows the portion of particles that have enough energy to react. That's all relatively straightforward. The stuff on the left, not enough energy. The stuff on the right has enough. But sometimes it's a head scratcher. And we have to bring particle physics into the equation to fully understand what's going on in the star. The electrostatic repulsion of like charged particles would dictate a much higher thermal energy for a particle collision to result in fusion. That means that this activation energy here isn't really here. It's more like over here. So why, I mean, this is, our star is balanced based on this energy, yet the energy required to overcome the repulsive forces of the like charged particles is way over here. So what's going on? Remember that the smallest of matter, the smallest particles, the smallest of matter is quite weird. They can behave like waves. Small particles can change position without actually moving through space. They quote unquote teleport into the new nucleus. Now, I'm using this teleport as a placeholder name. Put that in your brain, say teleport, and then take it out because it's not actually teleporting. It's just that the existence of these particles are weird. They can move through unadjacent space without traveling. I mean, they can move from point A to point B without traveling through all the space between A and B. They just can do it. And it's not actually teleportation. They're not doing it on purpose. It's just the nature of how they are. They are probabilistic in nature, meaning they don't have to be in a specific spot. They can be other places just instantaneously. The higher the kinetic energy a particle has, the more likely it is to tunnel, to do that transition from A to B without going through all the space in between. That quantum tunneling is required to make the fusion go. So going back to this slide again, so quantum tunneling is what's moving that energy requirement back down to here where we notice it to make that star actually start fusion and start giving off the energy that it does. So it's actually necessary for the star to function. Let's talk a little bit now the conversion of energy from the sun, what that fusion is doing for us, what's the net benefit, what's the energy we're getting out. And remember that E equals mc squared, that famous Einstein equation, that's not actually an equation, it's more of an equivalency. What that's saying is that energy and mass really are kind of the two forms of the same thing. Mass is almost could be considered a form of energy. So what? So E equals mc squared is telling us we're taking that energy stuff in mass and converting it to actual energy. So what happens when we do that? Well, the sun or sun model is burning about what is that? 700. That'd be 7 million. So 700 million metric tons of hydrogen is converted to helium per second by the sun. That's a lot of mass going from hydrogen to helium. 5 million metric tons of matter gets converted to energy. So of that conversion of 700 million metric tons, 5 million of it is getting converted to energy. Why is the sun not running out of energy? Well, because of this huge number that is the total mass of the sun. So even numbers this big are peanuts compared, not even peanuts. just tiny, tiny, tiny compared to this much mass. There's enough, in fact, there's enough material to go on for another 7 billion years. Here are something that tickled me because of my background as a chemical engineer. I dealt with mechanisms, and this is not a chemical mechanism, but a nuclear mechanism. And this is the nuclear mechanism for our sun, for our model today. This is the overall equation up here. 4 hydrogen, that's basically protons, but 4 hydrogen nuclei goes to 4 helium nuclei plus gamma radiation plus neutrinos. And this is the actual mechanism. This is the steps in the process. If you remember, know anything about mechanisms, if you start taking, you can actually start crossing off sums from either side of the equation. It ends up being that these added together end up equaling this mechanism. So this is the mechanism for our sun. However, it's not the only one that exists for all stars. For larger stars, there's also known as the Cno cycle. It ends up being a very similar, it ends up being very similar to the previous mechanism in its overall equation. 4 and 4. So 4 hydrogen protons goes to helium 4. Same difference here, plus gamma and electron neutrinos. However, you can see in the mechanism it changes differently. I mean, it proceeds differently, and it goes through oxygen and nitrogen and oxygen, and where's the other one? Carbon as a sort of catalysts throughout the mechanism. This mechanism also results in a different configuration inside the sun. So we just showed a little bit that some of our star models differ slightly. How does our sun compare? What we can't know versus what we can know. We cannot know the size of stars or their luminosity from knowing their brightness, because that brightness is distance dependent. Is that object that we're viewing, is that a very luminous but distant object, or is it a dimmer object that's closer to us? We don't know just by looking at it. Light's brightness depends upon an inverse square relationship. The star's brightnesses are classified by magnitude. Magnitude is a measure you'll hear astronomers and amateur astronomers use all the time. Stars' luminosities can be classified by a unit of power like watts or absolute magnitude. In other words, a star has a specific energy output, but that brightness that we see is dependent upon distance. What we can know when we're observing stars and the sun, black bodies, stars are approximately black bodies. That means their energy is being completely associated with the measured output of and there's nothing else going on heat wise as far as the sun goes. They're radiating what they're creating. They irradiate with color intensities with a predictable curve. Knowing that curve shape, the color index, we can predict the surface temperature of a star. So knowing a little bit math about how black bodies how much heat they give off, we can start predicting the surface temperature of the star. Knowing the surface temperature and the spectral type and luminosity class and a whole lot of physics, we can know stars' masses based on the color observations of a star. Knowing a star's mass lets us know many things about a star. So if you remember this guy here, which we'll look at very briefly, we can that same spectrum is drawn on this graph here, and this graph is the graph of black bodies and how they give off various spectra based on the temperatures that they happen to be at. And this can be determined actually in a lab before we apply it to stellar objects. You'll notice here that the visible spectrum that we enjoy here on Earth is drawn on this graph, so we can actually see where we are. And look at this. This is really interesting. This 600K line here, 6,000, excuse me, K line is drawn here. This 6,000 K line has a peak right in the visual spectrum. That's interesting. And we take a look down here, and we look at these various class of stars based on these various dominant absorption lines we see, but also about the color, as you note. And we notice here this class here, this yellow-white class around 6,000 degrees Kelvin, less like it showed here, has a yellow-white configuration, a color index of 0.3. Again, that seems kind of interesting. And you'll see why here I've been noting those places down here. Our model, our sun with a relative luminosity of 1, a relative mass of 1, and a relative radius of 1 happens to be in that 6,000 Kelvin degree range. All right. Here are some other well-known stars: Betelgeuse, Rigel, Polaris, Aldebaran, Vega, Sirius. These are all various temperatures and various luminosities. All these interesting ones happen to be higher than our sun luminosity wise. The masses are larger to very much larger. This radius on Betelgeuse, of course, the one that we thought might have been a couple of years ago, people were speculating that it might be ready to go on us, but no, it seems that it's they have an alternate explanation for the variation in Betelgeuse, so we're not quite thinking that it's about to blow up on us. But Betelgeuse here, that radius is huge. Would if it were here, would reach out almost to the orbit of Jupiter. So what do we do if we plot all of these stars, their various luminosities that we've calculated, the masses that we've calculated, and versus the color? We see this, we get what's called this HR diagram, where we have little red dwarfs on this side and massive blue and white stars on this side of the diagram, and the sun just happens to be somewhere in the middle of that diagram. This line here on the Hertzsprung-Russell diagram is this main line here is called the main sequence. All the main sequence stars are in this hydrogen burning phase on that diagram. The sun's a G2 V 5778 K. That's its various ratings. All these other stars, if you can see up here, have various other ratings and temperatures and luminosities, etc. Uh, there's other luminosity classes too. Here are white dwarfs, which we know are stellar remnants. Up here we have another type of star. These are giants, bright giants, supergiants. These are stars that are no longer on the main sequence. And we learned that the main sequence is hydrogen burning. So these stars are no longer burning hydrogen. In fact, these guys are not doing fusion at all, at least not in the normal process. So we talked about the main sequence, and we talked about other stars no longer on the main sequence. In other words, they are dying, or in the case of white dwarfs, dead. So what are red giants and supergiants? When the sun uses up its hydrogen fuel, it will collapse until its core gets hot enough and begins to fuse helium to carbon and oxygen. More massive stars will repeat this process. Where it stops depends upon its mass. Hydrogen, helium, carbon, oxygen, neon, etc., are concentric active cores found inside massive stars. And this is where we get back to the lithium and smaller. You notice that lithium and some of the lighter elements are not in this element generation. And that's what's happening in the universe. Lithium and are created by cosmic interactions in space. They are not created in the furnace of stars like so many more of the elements are. And again, the ones at the we'll get a little further into this discussion, but these guys, the larger concentrations of elements in the universe, are created in a stellar forge. Successive fusion types require hotter temperatures and give off more energy. The sun or star will expand to become a red giant or a red supergiant. Regardless of mass, even a much bigger star than is required, fusion stops at iron. Iron fusion doesn't happen. Iron takes more energy to create through fusion than it gives off. Therefore, it quenches the fusion reactions. Once the fusion stops, hydrostatic equilibrium is gone. The sun or star will continue to collapse until something stops it. And right here, that's a little bit of a cliffhanger, but just as an aside, after iron, again, those stellar explosions, of course, give off lots of energy, etc. So that's so few instantaneous types of fusions and reactions can create our elements. So some of the elements above iron, or the elements above iron are created by these violent explosions and reactions in the in the cosmos, and are created maybe as a result, but not directly by the stars. So what besides fusion stops this gravitational collapse? Remember, there's no longer any hydrostatic equilibrium. The fusion is stopped. It's either run out of fuel or hit iron. And now gravity is free to do what it's going to do. So what besides fusion stops a star's collapse? Well, first thing that will stop the gravity from collapsing the star into nothingness, electron degeneracy holds up white dwarfs. You saw the white dwarfs on that HR diagram before. Particles with like quantum values must stay separate. So the various uh, atoms inside the star or the various material inside the star must maintain separate quantum values. And the free electrons, again, this is a plasma, not the atoms, but in the plasma, the free electrons in such a star have to order themselves so that they can maintain this Pauli exclusion and provide a back pressure to resist the gravity. So the actual nature of the particles, their various quantum values, actually supply that pressure. If electron degeneracy isn't sufficient because the mass of the star is big enough and the gravity keeps pulling past that point, it happens at about just under 1.5 solar mass, the star will continue to collapse. Then comes a thing called neutron degeneracy. Now, neutron degeneracy is not very different from electron degeneracy. Again, it needs to, the various particles need to maintain, must stay separate, and in different quantum values must be separate. So the neutron star, so what's the difference between a neutron star and an electron star? Well, neutron stars get additional assist from the strong force. The strong force is a weird force. It doesn't only add, strong force is what pulls the nucleus of atoms together, but the strong force is not like gravity. It is a two-directional force. If particles get too close together, the strong force has a repulsive element to it. So it likes to keep particles a certain distance away from each other. And so the neutron degeneracy is aided. The reason why it's the next stop and isn't the same as the electron degeneracy is because it gets aided by the strong force. However, you can have even more solar masses than 3 solar masses in this stellar remnant. So beyond those forces, those opposing forces, beyond electron degeneracy and above neutron degeneracy, degeneracy, by the way, forming a neutron star. Beyond those two opposing forces, I've got nothing, and neither does the rest of the universe. The star remnant will continue to collapse and will form what's called a singularity or a black hole. So here are some stellar remnants. This is a planetary nebula, and right in there you can see a white dwarf. Here is another planetary, a nebula created by a neutron star. And we're not going to go into stellar remnants because that's a whole very interesting subject. That's its own separate topic. So that's it for my presentation. And I think we'll be going to questions next.
All right. Thank you so much, Paul, for your Thank you so much, Paul, for your presentation. Need to unwrap my tongue from around my eye teeth so I can see where I'm talking. All right. So I want to thank everyone on our online audience for coming in. We do have a number of questions. While we're answering these, feel free to add any more into the chats. So the first question we have is, hold on, where'd it go? It ran away. Oh, here it is. Speaking of solar activity, there was a news article recently saying that the aurora borealis would be visible in the area because of increased solar activity right now. Would it be visible from Jenny Jump?
The answer is they can be because it's happened historically, but the further south you get, the rarer it is, and it's pretty rare here in New Jersey. And historically, of course, the background light has been increasing, so it has to meet a higher bar the further we go through history. So I would say, and um, there's so many criteria that having to do with our not only what the sun is doing, but what our magnetosphere is doing, the surround or the magnetic field surrounding our planet. That I would take just a general news report with a grain of salt, and tune in maybe to space.com or another popular astronomy specific site to get maybe a better read on whether or not you will be able to see the aurora borealis from your location.
All right. So our next question is on the on the sun spectrum slide. Is there such a thing as a green or blue star that we have seen?
I'm not aware of what stars specifically have what colors other than, let's see if I can find that slide really
It was,
cool.
I believe it was towards the beginning of the presentation.
Yep, I mean, this is where we were talking about it, but there is a chart that I made. If I could find it that's too far. We were comparing stars. Here we go. And yeah, a green, I don't, oops, sorry. These are ones that I specifically know of, and not only do I know of these, but I have actually visually seen in my telescope these colors in the telescope. Green, I just want to say off the top of my head here, if you look at this chart here, and I zoom in here, you'll notice that our peak is very close to green. The peak amount of light that's coming off of our star is green. So we are very much. It looks like white to us, right? But that's because we grew up here. Our species evolved here, so we're just seeing what we think is light. So that's white to us. But the peak, what's that called? Range is in the green. Spectrum. So yes, there you have green as our star is putting out a lot of green. So our eyes aren't necessarily the same thing as measuring it with numbers. We might not see the green because we're just seeing our light. We're just seeing green light. So that's what's coming out of our star.
Cool. Let's see. Our next question is, so if there's space clouds filled with hydrogen, is that the same hydrogen we know of and use? And if so, in theory, could it be collected and used?
Could you read that question again, Kim? Because I didn't quite get the beginning of the question.
I believe this was referring to when we were talking about star formation and whatnot, when there's clouds of gas in space. So
Right.
if there's space clouds filled with hydrogen,
Oh, can
is
we?
that the same hydrogen we know and use? Is the
Uh,
first part of that.
Yeah, I think mostly the answer to that is yes, but various forms of hydrogen exist. You can have hydrogen ions, you can have various isotopes of hydrogen, etc. But largely, it's the hydrogen that we know of and are aware of here on Earth, and it's the most abundant element in the universe. Of course, the problem is one of logistics and whether or not we can go out and come back to one of these clouds. And unfortunately, um, uh, science fiction leaves us with a little bit of impression that we can travel to these places and go back. We're just technologically limited to our ability to do that. And at this point, no, it's still very unfeasible for us to travel interstellar distances in order to pick anything up. There's some serious issues with prolonged space travel or very distant space travel. Getting along through our planetary system, we're doing that well. Getting along in between the space in between stars, we are still a long ways off. So I wouldn't hold my breath for that one.
Yeah, so in theory, yeah, it could possibly be collected and used, but in practicality right now, it's no, is what I'm hearing. All right. So, were there any more questions in chat? I know we're just going to give chat a couple more minutes to get in any question. Um, while we're waiting on that, sorry, I was just typing into chat. I, I once again, I want to thank you, Paul, for a great presentation. Also, thank you for correcting me. I got to the BE and I realized, yeah, I don't remember what the E stands for. We're just gonna move right on through there.
Yeah, I think
Um,
Stevens is one of the, I think it's like one or two schools that actually give that degree. So it does send people for, when they see it, that a little bit of cognitive dissonance happens.
yeah, I was like, E, what does that stand for? And just couldn't think of anything. So, but I want to thank chat for tuning in. And sorry we could not have our on site presentation tonight. But like I said, considering I've heard a couple rounds of thunder and whatnot while we've been doing this presentation, I do believe we made the correct call. Um, Once again, if you guys want to check us out, do check us out on our website, uacnj.org. We also have our Facebook, Instagram, Twitter, and Discord channel. We are a nonprofit, and if you want to donate to help us keep offering free public programs and outreach, you can do so through our website. We also have a Patreon. Uh, an Amazon Smile setup. Um, it looks like our questions are done for tonight. So I want to thank you, Paul, again, and we'll have a good night, everyone.
Thank you, Kim, and thank you, everyone.